well and enjoyed your bubble tea. I'm going to start off nice and simply. We're going to look at what's driving the high-speed ecosystem, why faster and faster SerDes, why this move from 50 gig, 112 gig, 224 gig, and actually you see we're even seriously today looking how to get to 448 gig. We'll look at the market data. I know that my colleague Geg's touched upon a bit. The market data cannot be underestimated. It really is setting up where we can make our investments, not just in the R&D field, but critically, as Geg's highlighted, manufacturing. The scale and the ramp of manufacturing is going to be profound, far greater than we've ever seen. We'll then talk about the key technologies, what underpins the work we're doing today on 224 and we'll talk about Viavi ONE-1600, and then we'll move on 448 gig, and we'll have a quick summary. So the first thing I want to talk about is some of the big drivers towards higher SerDes speeds. We call this term sometimes beachfront bandwidth. It sounds very exciting, so let's talk about it. Silicon gives and delivers a tremendous amount. As we move to faster and faster nodes, we get more and more functionality, but the chips still get bigger. And often, even with the chips above the reticle limit, we can use interposers. We can get a lot of functionality. So today, the latest generation of switch silicon, we can get 100 terabits of switching on one device. Now that produces a lot of challenges because the area goes up for a squared function, but the size available to get the bandwidth on and off only go up linearly. This causes a mismatch. The silicon performance scales with the area, where the ability to get bandwidth off is just simply a linear function. So we get a mismatch. We get a gap between basic die perimeter, where we put our I/O, and the die area where wonderful things happen. Okay, so the I/O is actually almost taxed on the useful work the silicon can do. And so if we look today, and a great example is what the colleagues at Broadcom have done, their switch silicon, it's growing very rapidly. And of course, as many of you are waiting for your birthday present, Tomahawk 6 will be here very soon, and it will bring out 100 terabits of switching bandwidth. Okay, so how do we get that off? Okay, well, that's a big problem. If we're stuck with 50 gig SerDes, we need an awful lot of bumps. We have a big problem. Even today, with the 224 gig SerDes, we still need 512 SerDes. And 512 SerDes translates into 2,000 bars because each SerDes is an RX and TX, it's differential. So if we try that with the P version of Tomahawk 6, Peregrine version of 112 gig SerDes, 4,000 bars just to get the data on and off. Okay, so clearly we need faster and faster SerDes because very quickly we're going to have 200 terabit silicon coming out there. So it's a challenge. We just can't get the bandwidth off. Okay, now there's lots of novel technologies coming up. Sony's CPO and co-packaged copper will play a huge part. But today, high-speed SerDes still dominate. It's the most friendly way to move bandwidth around because we know how to move SerDes and use them to move over common traces on PCB. It's a very good way of building things. There's approaches like co-packaged copper, flyover, co-packaged optics. At the moment, there's still seen as emerging technologies that come with a cost. So high-speed SerDes and beachfront bandwidth is a big deal. Now, not all beachfront bandwidth is the same. There's actually three things we can talk about. There's the die beachfront. That's the most expensive real estate. That's like the boss of the company who lives directly on Manhattan Beach. He can walk out of his mansion straight into the beach. And then there's the second boss, the Ben, who has a house maybe one block from the beach, and he has to go through a little bit of streets and walking. It's a little bit like the signal integrity of going off a package. And then finally, there's guys like me who live a long way from the beach. We've got to drive on the freeway and go through the rules. So we've got a lot of impairments in signal integrity to get to the beach. That's like the front panel, you see. So all of these have limitations. We can address some of them. Die beachfront is certainly a big deal. But interposer beachfront, that's where CPO and CPC, co-packaged copper, are a big deal. Midboard, we have midboard optics, flyover, but the front panel today still dominates. Most of the switches shipped today are using front panel optics. Even though Gates have a great picture of the NVIDIA Spectrum switch with the convex optics, that's still a little unusual. Most people still like the concept of pluggable optics in the front panel because it gives them the flexibility to support DAC, linear, retimed optics, even coherent optics. We still have customers today who really mix things up with their products. Of course, it allows customers, especially the telecom enterprise space, to configure their products as they need them, whether it's coherent, linear, DAC, or even pay-as-you-go as well. So front panel pluggables are still very, very important. And that's why there's still a lot of effort in addressing this in the channels. So now let's look at the market data. A little bit of background, why Gates faster SerDes. Now let's see what the analysts think. So all the graphs look very exciting. 400 gig, 800 gig, they were pretty exciting. We had about 5 years from the very, very early 400 gig to when we started 800 gig. We built our first 400 gig test set back in about 2017, about 2 years before standards, based on this gigantic thing called CFP8, if any of you remember that. It was a very early first generation 400 gig optics. It was about the size of a cell phone. It was pretty big. But 400 gig really took off with the hyperscalers adopting QSFP DT at scale. And that's where you can see the ramping up there. 800 gig was a bit of a silent force. It came along really out of nowhere. All of a sudden, we woke up one day realizing somebody was buying lots of 800 gig modules, hundreds of thousands a quarter, so 10,000 a quarter, but it wasn't really an open play. In fact, it was the AI ecosystem. They had to adopt this type of fabric very, very quickly. And you can see the 800 gig has been a steady ramp, and they actually will overtake 400 gig next year. Now, the big news, of course, is the quick move from 800 to 1.6 terabit. Only about 2.5 years. It meant a double SerDes speed, a lot of new technology, certainly pre-standard. We've already started seeing the build of 1.6 terabits a day. Early market figures show they expect to ship roughly 500,000 optical plugs to 1.6 terabit by the end of this year. So something that's still on a draft 2.0 for standards is already shipping those fixed figure numbers. And that's going to ramp very aggressively. If we look at the ramp of 1.6 terabit, it's very, very significant. It's going to, within 3 years, it's going to cross the previous rate. It's far faster. The ramp is faster and quicker and greater in scale than anything we've seen before. You can see millions of units. So the peaking there, about 28 million, peaking there, about 38 million. This is going up. This is, of course, it's predictive, but this is what we have to scale with. All of this, 3.2 new technology, around starts 27. We already have customers today who are asking me to deliver 3.2 terabit test solutions within 20 months. And it's a new and disruptive technology. But today, we only focus on this green line because it's a very long life. And certainly for the next 6 years, we're going to see a tremendous amount of 1.6 technology, still using prepared. So why is this a big challenge? There's a couple of things that are very new to all of us. First, the speed is becoming faster for new generations. In the past, we had 4 or 5 years to generate 2 speeds. So that gives a chance to do some experimental work, maybe 2 or 3 generations. Many of you might remember last 100 gig. 100 gig, we had about 3 generations. We had CFP, CFP2. Finally, we settled on QSFP28. We started seeing ramping. So we had we certainly had 5 years of those beautiful products by us to get the integration and volume there. But then 100 gig is just off. 400 gig is quicker. Then with 800 gig, 1.6 terabit, day one, we have to ramp with the right form factor. We had no luxury of big fat form factors We had to integrate into their OSFP 1600 day one. Okay, so about 2 years now between speed ramps. The time to market is much quicker. 2 years actually isn't a very long time to develop a product. You have to do an architecture, you have to sort components, start building it, and then bring it to market within 2 years. That's very, very challenging. And you haven't got time. If you screw up your PCB, if you screw up your ASIC, it's not a happy ending. Okay? So the time to market is far more aggressive. And the time to test, time to develop, time to manufacture, all has to fit in that 2-year window. If you're late to market by 6 months, your competition has eaten your lunch. Okay, so simple as that. First to market is very, very important in this space now. People that are successful, we see this with the module companies. When you want to be the bride of NVIDIA, you better turn up on time with the right product. If you are 3 weeks, 6 weeks late, you've missed the dance. Okay? It's like the pretty girl in the school dance. If you're late, you don't go, you don't go. It's not a happy evening. Okay? You have to get to market on time. Very critical. In 2 years, it's not long. It's not like 5 years, 6 years. This is a huge challenge for a return on investment because you've got to get the product right first time. And the product may only have a lifetime of maybe 3 or 4 years. Okay, because the next speed is coming along. Also, the big challenge, which gets talked a little bit, is about the ramp production. The scale of the ramping is far greater than we've ever seen before. If we look now with 400 gig, the people that built up the factories, the slow ramp, so every couple of months they could revisit the supply curves, demand curves, build out more space, build out more test runs. And of course, every time they develop a new factory. We're now seeing this ramp for 1.6 terabit. It means the people building these modules not only have to build a plan to launch 1.6 terabit at huge numbers, there's several tens of thousands a month. At the same time, they've got to keep up their production line for 800 gig. How is it line? You can't build a big factory to do this in 6 months. You have to utilize every square centimeter of floor space. It's valuable. This is why Gex and his team have spent a huge amount of effort, not just making very high performance switches and power meters. They have to be super dense. You've got to get one test stand now can't be dedicated to one module. That test stand has to get from 4 or 8 modules, and it has to get tested quicker. Because to support this ramp, the old ways of repurposing a test stand from the 100 gig days, you're not going to get very far. We did see on the transition from 10 gig to 100 gig, 100 gig to 400 gig. Many companies took their old test stand, put in a faster scope. We can use it because it's the same thing. It's a power meter, it's a noster, it's a source. That can no longer work. Of course, the test stand works the test stand, but it's about 10 to 50 times too slow to meet that number. And it's going to cost you too much in power and floor space. So people now are having to revolutionize their test stand and test stand concept to get the ramps needed by the hyperscalers. The ramp, look at this now, it's far different from what they had even 2 to 5 years ago. You have to design in a plan to scale production, whether you're building switches, because behind every optical module is a switch. And that switch will also run at the same scale. When Meta are building out their Prometheus project, that's going to be an awful lot of switches to connect those AI together. And you have to be able to build and scale and test, not only get the product to market and win the beauty competition, you've then got to show a plan to scale and ramp at that pace. And that means everything from metal, power supplies, fans, tested switches. Optical modules, that means test stands that can deliver thousands of modules a day in throughput, in the smallest compact space. Because if people can't build factories, it's not just 2x faster speed. There's new things, new speed, making this even more challenging. Okay, so new technologies. What's happening? What's underpinning this big wave of 224 gig? So I always like to start with the optical module. Typically from our test measurement unit, the very first thing I plug in into our new speed, when it was plugging in 2040 years, there were 22 I plugged in the first 100 gig module, or a year ago, they plugged in the very first 1.6 terabit thing. It was not a module. They are typically the leading thing we see first in the technology world. Of course, it brings together a lot of technologies, especially the high-speed DSP, the 212 gig servers. Lots of things have to happen to make this work, and it's a very good indicator of what's going to happen in the market. I can tell you, I've plugged in the past year, we've been driving our 1.6 terabit, I've plugged in at least 10 different vendors' optical modules based on 3 different DSPs. We're still in the early days of plugging into 1.6 terabit switches. Anyone here has got a Tomahawk stick switch they want to test? Let's talk. So the modules are very early on. They're a very good indicator of where the market is and the problems we first face. So it's the key area of validation first. Typically, when we bring out a product, our first set of features are focused on the physical layer and module testing. Then we round out layer 2 features, layer 3 features, and extended features. But day one, we have to be prepared to test the modules and the technology we have. High-speed servers, BER, FEC profile, lots of things around the seamless, the Photonics, as Gabe has told you, lots of testing there. The modules for us are a very good indicator of the problems we're to face. So over the past 9 months, working with many companies, we've learned an awful lot of ways to prepare and the technology struggles we are facing. The modules themselves, well, they consist of different flavors. We have OSFP, that's dominant now. We no longer see there's no human drive for QSFP DT at 1.6 terabits. Different flavors, writing using, interrupting. This is more just for reference. I think it's not too critical for the high-speed side. But there's lots of new building blocks. 400 gig to 800 gig was pretty boring. 400 gig was basically glued together, then we got 800 gig. We actually didn't get much from IEEE. We used the same technology. The map was very similar. It was just a 2 400 gig maps glued together. We did double the service speed, but the 50 gig to 112 gig service, that was relatively simple. It was not a big deal. We didn't see too many problems. They're both based on PAM4, both based on the same SerDes technology. It worked very well. 2.4 gig is much harder. The actual SerDes rate is 212 gig, PAM4, and it has the overhead of a read-stolen effect. There's always a read-stolen effect in there to protect the interest of the electrical part of the interface. On the optical side, it runs faster 226 gig. That's because none of the optical interfaces use an additional FEC in effect, because sometimes the optical interfaces distortion, PAD, channels, multi-reflectors can cause additional budget constraints, so we need a bit more FEC gain to close the link. So typically, interfaces over 2 kilometers, which you do find in some hyperscaler spaces, they do need that additional FEC gain. And that's hence the 226 gig. Single marks, that's a big change. In the past, when we created those PAM4 signals, we went up from inside the FPGA. We would mask them bitwise, very simple bit masks, ping, 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 very simple design, pretty reliable. But we actually lost some of the code gain available. So in the 200 gig lane, we've moved to what we call single mask. This means much more intelligence in the gearbox. It's a very big change. We had to move away from simple masking because we actually lost some coding gain. By moving to simple masking, I'm trying to illustrate it here. This is my cartoon is already good. This is actually directly from HHG.3. You can see how it comes together. Here's a cartoon here. Basically, you're masking together the 10-bit text and mask to create a much more robust error-proof on the line side. So that's very new as well. That has a lot of complexities and logic. And then also impact interoperability. If you don't get your bit masking, simple masking right, get them mixed up, then the systems can't talk to each other. And we actually did have to take that in some of these systems. The form factor with OSFP 1600 is dominating. It's a very good form factor. Really, the QSFP camp has gone very quiet now. Most OSFP today have one back there is you've got literal heatsink, probably good to about 35 watts. They will be riding heat sinks as well. They're going to be used typically in NIC AI applications, but with the flat top, they also hold problems with very high power hearing applications. There's work being done today in installing OSFP MSAs, looking at power certainly above 50 watts. Although that means moving away from 3 volts on the power roller through to 12 volts. 1.6 terabit is coming. Although it's not the primary driver today, most of the people working with today are using that 1.6 terabit port as 8 by 200 gig, maybe 4 by 400 gig, maybe 2 by 100 gig. 1.6 terabit though, that will come. Some customers are very keen there. You know, Google's one that really wants to move very quickly to 1.6 terabit Mac, but that has changed. Up until the time, with PAM4, we've actually based everything on 25 PCS lanes. But when we move, we've already got lots of them. We have 32 PCS lanes at 800 gig. Moving to 1.6 terabit, that would not be scalable. So actually, we move to 100 PCS lanes only for 1.6 terabit. That means we have 2 things that operate in parallel. If you use the port in an 800 gig mode, 400 gig mode, you use the 25 gig PCS coding. And then you move to 1.6 terabit, you move to 100 gig PCS coding. And this again has some implications for system design, even design gearbox and things. It's important again to be aware of that. It's all laid out in 802.3DJ, but don't run on around 25 gig PCS layers. You won't interoperate with them. So the big 4 things that will make a big impact at 1.6 terabit. The most profound is going to be intra-sublayer link training. At 800 gig and below, we always have to solve the problem about we have different losses in PCB traces. If you're building a big enterprise switch, you will have different lengths of PCB traces. Some of the ports in the middle of the switch have a fairly low loss between switch ASIC, the OSFP connector. Other signals that you routed around the back of the ASIC, they may have lost into the order of 20, 24 dB. So very significant differences. To mitigate that, typically the system would have traces or channels which you designate high loss, traces and channels you designate as low loss. And basically, at one level, you would basically work out to have a high loss or low loss channel, consider the corresponding amount of preemptive for the module and ASIC. And that worked very well at 50 gig. It started to have some issues with 112 gig SerDes, where sometimes a channel can be too short, like on a NIC, you could overdrive the receiver, and it really didn't optimize the TX characteristics to give the very best performance. Because a high level is very binary setting. When you're varying channels, you can go from 4 dB to over 20 dB. A bit more granularity can drive better performance. The IEEE took note of this, and DJ came up with the grand concept of intra-sublayer link training. What it really means is between the plug, the optical module, and the ASIC, you would leverage the link training technology we used in DAC. That means that there's a small protocol running when the device is plugged in, and there'd be an exchange using very small technology, link training from DAC cables, which would allow you to optimize your TX preemptive coefficient to give you the best BER performance for that link. So the idea would be that you would no longer need to have a low loss to high loss link. You would have per link training using intra-sublayer link training to give you the most optimal BER using the correct coefficient for your TX premises. So TX will take care to make the receiver have to be the best, least work to get the best BER performance. That's building work, but it's actually there is a few challenges with it, but the colleague in the IEEE have been working very hard. It does involve a little bit of work also with the ISO and CMOS support that as well. And certainly for anyone involved designing modules, anyone designing switches, you will need to take care of this. This means additional firmware. It's a lower layer, which must work. It's very challenging to debug this. We at Viavi have a lot of experience debugging DAC cables. DAC cable, that linear trading technology, hasn't really changed since the 100 gig days. But guess what? Every speed, we get a phone call from a customer saying, well, once to enter this DAC, can you help us? We have a special debug tool where we look at the different messages going back and forwards and help people debug their data links. And that's been an established technology we've had for 5 generations now. This is new, and I think, in my view, industry-level link trading will be one of the biggest headaches people face. If you don't get it right, the modules won't talk to each other, so you don't get any training out at all. If you don't get it perfect, you might take issues with burst errors and other things which are very, very difficult to diagnose. So intra-sub-layer link trading will be a new and a little bit scary challenge in the industry. But don't worry, we're on it, and I'm hoping we'll have some, we've got some pretty exciting ways to deal with those issues. But it's something you need to be aware of. You need to think about when you're designing a switch, your module, your NIC card, you need to know about this stuff. Read the chapters very carefully, make sure you understand it. It's a little bit funky, and you also need to pull in some of the work in CMOS as well. The next big new thing is the inner FEC. So not to links, and we'll see them later, the additional coding gate. Now, rather than changing at system level, the FEC needs to be perfectly empty. The idea is that ASIC switch system almost uses read-only FEC. That protects the electrical load. Depending on the PMD, if you have a 2 motor link, you can have an additional FEC inside the optical module. So a FEC high with a FEC. And typically for the 2 kilometer links it's needed, it uses a new coding scheme, soft decision FEC, but it lives inside the module, but it still matters to you. If your link isn't working very well, you need to know why. You need to extract data from that module over the I2C to validate your link. So that's going to add complexity as well. I talked briefly about 100 PCS lanes, which will be using 1.6 terabit. And simple mask, it's also very new. Bit masking has been used in below. But for the 300 big layers, we're now going to 10-bit simple masking. And yeah, it's one of these things that sometimes not everyone's ASIC works the same. Okay, so be aware of that. It involves big machines and lots of things. If it doesn't work, you have tremendous interop problems. So here's some pictures just showing some of the new stuff. Here's the electrical connections, optical mediums, and again, there's PAM4, there's fiber, there's WDM, there's incoherence. But there's 3 FEC approaches, end to end, encapsulated segmented. It's not as simple as you think. The switch, ASIC, hostess takes care of the end-to-end FEC, basic system concept here. Then, depending if it's a clear interface or if it's WDM interface, you might get one of these 2 FECs encapsulated or segmented. And again, do become familiar with the courses, okay? Don't mix your FECs up because they won't interrupt them. These are a couple of things that we've learned over the past 9 months to run the Viavi 4 gig. Certainly, on the SerDes side, that's where we've seen the most issues. Forward signal integrity, equalizer tuning has been a fairly significant headache. Without ILT, we have to go to manual. There's no more big guesses in this. And certainly, I've spent more than enough long hours in labs in Wuhan and Chengdu and other places doing manual linear tuning. It's something quite challenging. IoT would help a lot. And the challenge, of course, is that you might think you've got a good link training when you manually, but then every half an hour you get a burst error. And you only really see the burst errors if you're using framed FEC traffic. It's very difficult to see burst errors with just a pure VRV stuff. They're using real data later on to prove that. The margin plays into that. You might get a good VDR, but there's no margin there. There's someone drives their truck past or a butterfly ran to the car outside. You get a burst of errors, and that's the worst in the world. You think that you're good, but actually every couple of hours you get some bad errors. That's very hard to function. Effect high, that's something we haven't seen too much of yet. Some modules are beginning to come up. You might hear around that. This is a big one, ILT. It's still being worked on a little bit in the drafts. We expect to see the first silicon supporting ILT around about November. And there must be lots of fun, or lots of very late night coffee drinking. 1.6 terabit app, that's going to be a new thing as well. And there's this old favorite, module firmware, power and cooling, and of course, which Jake's talked about, production manual scaling. This is huge. This is far more aggressive than we've ever seen before. So these are the big things we have from a test and measurement point of view that impact on the 1.6 terabit system. So let's look at some first experiences. So we brought to market our very first generation 1.6 terabit tester about a year ago. Okay, it was actually built onto VCon. They locked me in the lab, and we spent many hours bringing them up. And it was very touch and go because we didn't really have any TQTs. We were sort of guessing what things like. We actually got hold of a 1.6 terabit module 2 hours before the VCon show started. And we made a successful demo of 1.6 terabit, and we're now actually on the second generation. So we actually, in that 1 year, we've gone from very early samples to actually second generation of 1.6 terabit testing. It's been a very busy time. We've worked with multiple module vendors, multiple DSP vendors, multiple system vendors. In every case, they have successfully brought products to market. I think it's safe to say anyone who has a working 1.6 terabit thing on the market today, they're using this box because it's the only one that's been available over the past year. We're now on the second generation. We've learned a lot. That knowledge comes out with new features, higher performance, and quicker test time, more insight from test time. We designed it day one to meet the needs of the broader ecosystem. We know the physical layer is important, and we typically meet the optical plugs at the first ecosystem. So we wanted to make sure at release it's ready for the use of the optical module vendors, but would scale to the needs of the switch vendors. Hence, 100 terabit about. That's architecturally very demanding. We had to build a system that could scale 64 ports of 1.6 terabit and hold coherence across those ports to 1 nanosecond. That means any port, any packet, we know where it's been to 1 nanosecond resolution. That was actually quite challenging. We've done that. So we've got the ability to fully load 100 terabits of fabric today at 1.6 terabit or 800 gig using this architecture. Results have been very good. Since that VCon time, I've been very busy, and we've learned a great deal. Key areas, error baseline is critical. You've got to really understand what's your error fingerprint, what's it really look like. And you only can really do that with effect. BER can be very misleading. I'll show you some things later on. Equalizer settings. You have to be able to understand where you are in the equalizer tuning stage. ILT isn't here yet, and even when we get ILT, you're still going to have to debug things manually. ILT may not get them right. Power management and cooling. So we have, of course, we're working with finals today, coming out typically now with 30 watts for 1.6 terabit by interface for DR8. But we've also successfully worked with people developing coherent modules over 40 watts. And we knew that eventually people with CR might be getting to nearly 50 watts. So we designed ports to handle up to 50 watts, especially in terms of power delivery. So here's the point I think is very important. Both these graphs were taken with the same optical module in the same channel, both electrical optically, nearly at the same time. Okay, so what's the background? We were working with a customer, and they were bringing up their module. And when we looked at an unframed BDR, we were getting about 10 to the minus 8. 10 to the minus 8 BDR using a PRBS 31Q is pretty good. And they should never have link flaps. Okay, it should be a very reliable link. But yet, when we put it into live traffic mode, we got a pretty horrible picture. Very, very, very long vector going in uncorrected level. So something is going wrong. Okay? BDR said everything's good, but when we looked at using the threat analysis tools, it was pretty clear something was badly going on. In fact, using some other tools we've got available to us, the equalizer from the module to our receiver was overdriving. Without an IoT, it had expected a 16 dB channel, so we're actually getting this in clipping, causing this very, very long tail by burst-overs. But it still happened rarely enough to make it about 10 to the minus 8. When reaching an equalizer maximum, look at the result. Maximum 4 errors of the code words, that's a good performance. Okay, actually, you even got better than that. Same module, same channel, nearly the same BR. Both looked at 10 to the minus 8, plus minus. But that's a big difference in performance. You have to look in the frame domain. Unframed measurements are really misleading. They were bad enough at power for 50 gig, 100 gig, 212 gig. If you do not look in the frame traffic fed domain, you will get badly caught out. You can go out there thinking your product's really good, 10 to the 8, 10 to the 9. We actually have modules where we got to 10 to the 9, but when we looked at they were still getting isolated error bursts down here because they were ever so often to the left. Now, some of them the faster DSAP, especially they may even be faster edges or shorter channels and link casts. This is a problem. You must perfect domain. You must understand what the receiver is doing. We've taken a lot of time, so we've made a lot of improvements. So today, typical performance we'll see now our test set. We're getting around about 10 to 13 waiting levels on channels. This is a real optimal module. This is a real optimal module. Untested set, it's been tuned. So the test set performance is better than 10 to 13. Okay, that's a treating trial today. And that only happened after a lot of experience, and the second generation of silicon. And we actually want to do better than this. We want to give you the very best performance we want. One of the things we want to do at Viavi is to make sure you're testing your DUT, not testing the tester. Okay, so you're getting something that is, you can really understand every error, every bit, every burst is the DUT, so you can actually make meaningful diagnostic analysis. 212 is boring. I mean, you've done it, right? I've been shipping it for a year. It's like, you probably get it on eBay now, TikTok or something. What's much more exciting is 448 gig. We're working on that now as well. Whereas with 448 gig, we're very much in the validation phase, particularly the introduction phase. 448 gig is still very much research. People know the next generation test approach to these things. They're coming to us and saying, we need 448 gig. How can we get there? We want to know the beachfront bandwidth issue, get it to bandwidth off the silicon, off the interposer, the front panel, 212 gig will not go for us. Is this typically what we're looking at? Lots of new things. We're typically looking at substrate, interposer, co-packaged copper, flyable cables, because it's going to be very difficult to transfer 448 gig. Suddenly we get out this breakout region. 448 gig is going to be very challenging. Probably moving to a two-part connector and the optical plugs. So direct channel copper to people like Tyco have been using some models there. We're making from that. So we expect to see co-packaged copper uses two-part connectors. We expect the first system is early 2027. The LIF framework is underway, so we are very good supporting possibly perhaps fixed, even planning might be used collectively, although one vendor is using them more in a different way. Bandwidth limitations in the PCB. We really want to keep bandwidth under 100 gig. Everything rests. It's very difficult to move anything through a connector as an electrical bandwidth above actually about 70 gig. Photonics has a few issues. So Photonics can still work at PAM4. Home package copper will play a very big role. We believe two markets and modules. The finger white is a big deal. If you take in QSFP DT data link gate, set the link up, look at the BR. If you then touch the module, move it backwards and forwards, the latching mechanism will cause connector white on the panel card. So you might be moving a few fractions of a meter, but the mechanical tolerance is built out, you will see a change in BR. That is catastrophic at 112 gig, more so 212 gig, more so. You can't afford it for very good. You cannot have one you connect anymore. It's too apart. So, two part connectors probably there. Big design for level optics still, people want them. It's also push for high density level formats as well. And package will play a role. So, of course, here I've illustrated this with code package copper, but of course, that can equally be, as Gates was highlighting, high density CPO. And then we want to go to an optical link as well. So, I think I've come to the end of my time. Let's review things. Faster speeds, quicker technology moves. Our cycle now is collapsing to 2 years. And that 2 years is not only bringing the product to market, it's dealing with substantially new technology. Not just a 2x speed increase, lots of new complex technologies. Even at 212 gig, we are dealing with interesting training, 100 PCS, new types of connector technology, new types of platform technology, lots of new things hitting you at the same time to 2x speed increase. You cannot afford to be negative on. 2 years is not long. At the same time, it's not just the time to market, it's that round. That round is far more aggressive. ROI becomes critical. PAM4 DSP equalized. I'm an old guy. I remember old analog CTLE. It's very simple. It didn't work. I played the capacitor or the chain in the motor. Now it's all in the magic DSP code. I'm not sure if anyone knows what it does, but it sort of works. But the DSP is a lot harder to debug, cover PAM4. Of course, we have much more technologies. Closing a 40 dB channel would not be possible with analog CTLE, but for DSPs today, that's what we see to be with John sticks, its performance. Many new features coming in there. IoT, as an effect. OSSP dominates. We can no longer count errors. Unframed BR doesn't help you. You need insight, deep insight with live tracking. So you want detailed error fingerprints in your frame tracking. That's something we certainly have a lot of features for that in our test sets. We have Viavi in the market now for over a year. We've been shipping 1.6 terabit now for nearly a year. We're now in the second generation. One of our secret stores is our very experienced support team. We have dedicated team of system engineers who are not just promoting the stores. We make sure they get exposure to all the global customers. Best knowledge, those teams bring up systems in China, so as they get quickly around our Viavi expertise. That comes together with our products, comes together with our engagement with our customers. It's not just a metal box with very good software, it's actually real people who can help me and give you guidance to choose your systems. We've got lots of unique applications. That 1 year has been a very busy year. We've actually used it to refine applications originally developed back in the day, 100 gig, 400 gig. Those applications have been enhanced. We're actually developing new applications for such things as IoT. So lots of unique things going on. So I think I'll end there. Thank you very much. You've been a good audience.